Hello, I'm Carlos Rosas and this is the CRS channel. Uh, we're going to continue with the physics problems in kinematics. Uh, uh, we're going to start working on problem 4. Before beginning with problem 4, I want to rectify something here. This datum here, let's say it's where in which I mentioned that normal person could jump 0.25 meters to 0.35 meters without running to gain impulse, corresponding to the normal person. In the case of high performance athlete, uh, the jumping height could reach 0.5 meters or maybe more. That was when the technique used for the uh, high jump event in the early 20th century was corresponding to that of a standing jump. That height increased beyond 0.5 meter value when the techniques evolved and running to gain impulse was used as part of the high jump techniques. Okay, now we can start with problem 4. Problem 4 corresponds to the fact that earthquakes generate various types of waves, and the most known are the P waves, P standing either for primary or pressure, and the S waves, where the S would be standing for secondary or shear. In the Earth's crust, the P waves travel at about 6.5 kilometers per second, while the S waves travel at about 3.5 kilometers per second. Of course, these speeds depend on the type of materials the waves travel through, so they are just approximate average values. The travel time differences, in which travel time means the time it takes the waves to travel from the source of the waves to the detecting stations. Such differences between these two waves give an indication of the distance to the focus where the earthquake took place, that is, the source of the waves. This point, known as focus, is also known as hypocenter. Okay, if such differences of 33 seconds, how far away is the focus from the detecting station? So we have a simple diagram here in which we have the focus F within the crust. This is the Earth's surface. This is the surface of the mantle. This is the depth h of the focus. E, corresponding to this point here, is the epicenter. S is the point corresponding to a specific detecting station. D is the distance from the focus to the station. And delta is known as the epicentral distance from the epicenter to the station. Tp is the travel time for the P wave, Ts is the travel time for the S wave, Vp is the speed of the P wave, Vs is the speed of the S wave. So the travel time difference, delta t, is equal to Ts, the travel time for the S wave, minus Tp, the travel time for the P wave. Okay, so assuming that these speeds for the P wave and the S wave are constant, we have that Ts equals d over Vs and Tp equals d over Vp. So that delta t equals d times Vp minus Vs over Vp times Vs. So that d equals Vp Vs over Vp minus Vs, that multiplying Ts minus Tp. So if Ts minus Tp is 33 seconds, Vp is 6.5 kilometers per second, Vs is 3.5 kilometers per second, that gives us that d is 250.25 kilometers. So, assuming a flat Earth, as is shown here, the distance d is equal to the square root of the epicentral distance squared plus the depth of the focus squared. So if h equals 33 kilometers, that is the thickness of the crust, then the epicentral distance is 248.06 kilometers. If the depth is 0, that means that the epicentral distance will be 250.25 kilometers. For a travel time difference of 60 seconds, and that'll give us that the distance will be 455 kilometers. That for a depth of 33 kilometers will give us an epicentral distance of 453.8 kilometers. Okay, this will be used later on explanation I will give on a rudimentary approximation one can make to determine the coordinates for the focus. Of course, assuming that the focus is within the crust. Okay, now we go to problem 5. The car goes along a line at constant acceleration. Times t1 and t2, its positions are x1 and x2, respectively. Prove that the acceleration of the car is given by the formula a equals 2 times, on the numerator, x2 t1 minus x1 t2, and at the denominator, t1 t2 times t2 minus t1. Okay, so we use the formulas for the position in the case of constant acceleration. x1 equals v0 t1 plus 1/2 of a t1 squared, and x2 equals v0 t2 plus 1/2 of a t2 squared. Dividing by t1 for x1 and by t2 for x2, we have that x1 over t1 equals v0 plus 1/2 of a t1, and x2 over t2 equals v0 plus 1/2 of a t2. Subtracting these two values, these v0's cancel out, and we have x2 over t2 minus x1 over t1 equals 1/2 of a t2 minus t1. So, simplifying the fraction, we get x2 t1 minus x1 t2 on the numerator over t1 t2, which is in the denominator, equals 1/2 of A, T2 minus T1. So that A equals 2 times x2 T1 minus x1 T2 in the numerator and T1 T2 times T2 minus T1 in the denominator. Okay, now we go to problem 6, which will be solved in the next video.